All right, good morning, guys. Today we're going to be covering 8.1 Introduction to Circles. This is the first video in our circles unit. So this unit's going to be all about circles, all their properties, and the various ways that we can use them. So with that being said, let's go ahead and get started with some definitions. So the first definition that we have circle O. So if we look at this circle, the symbol for circle is just a circle with a dot in the center, and that's how you can write circle shorthand. Followed by the center of the circle. So if you have a point in the center of your circle, that's how you'll label it. So you'll call it circle, then whatever point is the center. So that means that O is the center of the circle. Again, circle O, that's just the name of the circle itself. Next up, we have concentric circles. Those are circles that have the same center. So as we look over at the circle on the left side, we see that we have a smaller circle in the center, then a larger circle around it. If we look at this, there's no other point for the larger circle or the smaller circle. They both have point O as the center. And since they have the same center, they'd be called concentric circles. These two are probably some of the most important terms that you guys will see on this slide. They'll cover the basics of circles and how we name them as well. Next up, these last three terms all are going to deal with this bottom circle, and they deal with where points can be found around the circle. So first off, exterior. Exterior just means outside of the circle. We have point Q as an example of an exterior point. For interior, that is inside the circle. Point P is one example of an interior point. Point O is also an interior point. Those are both inside the circle. The last term that we have is on the circle. That would be point N. That is a point that is actually on the circle itself. It's on the edge of the circle. So if you have a point on the circle, that would be on the edge. All right, next up, let's go ahead and talk a little bit about circumference and transformations with circles. So the ratio of a circle's circumference to its diameter is equal to pi. Now again, ratio just means division. So we see that we have division here of circumference, the distance around a circle, to its diameter, the distance across the circle that goes through the center. If I take the ratio of the circumference over the diameter, it will always be equal to pi. And the reason for that comes from our circumference equation. Circumference is equal to diameter times pi. If I want to get pi by itself, I just divide both sides by the diameter, and that'll give us pi is equal to the circumference over the diameter. And that's actually how they discovered the number pi. They measured out the distance around a circle using a piece of string, and then they measured the distance across the circle that goes through the center with that same piece of string. And then they took the ratio of those two. And they kept getting numbers that were closer and closer to pi. And granted, they did this in ancient times, back when they didn't have rulers or anything like that. They would just put a piece of string on one point, have it go all the way around, measure where it reached that initial point once again, and then they'd take the piece of string, straighten it all out. Whoops, sorry about that. They take that piece of string, straighten it all out, and then they'd measure that piece of string. From there, they just measured the diameter, and then they would divide the two, and that would give us pi. Now, transformations. If we think back to transformations, transformations were in Unit 1B, and we want to think about what transformations make sense within the circle. So the first three that we have are rigid motions, all from Unit 1B, and then dilations was from Unit 6. So let's go ahead and think about if these make sense within the circle itself. So the first one that we have is rotations. If I rotate circle P about its center, would anything change with the circle? Well, no. The point that's on this axis, on the y-axis here, would just rotate around and it'd still be on the circle itself. So the image in the pre-image of the circle would be the exact same. So rotations don't really work too often with circles unless I'm not rotating around the center of my circle. If I was rotating around another point, then yeah, it would change where the circle is located. But oftentimes, if you rotate around the center, it won't change anything. Next up, reflections. If I reflect across the y-axis, would this change my circle? Well, I have circle T here. If I reflect across the y-axis, it would turn into circle T prime. And of course, these are different circles. They have different points, right? They have different ordered pairs. Granted, the distance between the points, the betweenness, all that stuff remains the same. However, it does change positions So therefore, a reflection would work. That is a transformation that makes sense with a circle. What about a translation? Translation is movement along a vector. Would translating circle Q along the vector 1, -3 change anything about circle Q? Well, if I translated along the vector 1, -3, I'd move to the right 1, then I'd move down 3, making Q prime. So yes, this would change the circle. Again, it's not going to change distance or betweenness or anything, but it will change the position of my circle within the coordinate plane. Then lastly, a dilation. A dilation. If I take a circle, circle R, and dilate it from the origin, would that change circle R? Well, yes. If my dilation is larger than 1, it'd be an enlargement. If my dilation is smaller than 1, it'd be a reduction. But yes, this would create another circle. And what can I call these circles? R and R prime. What type of circles are they? Well, they share the same center, so they're concentric circles, which is what we just learned about. So these circles are in fact concentric. So recapping all of this, once again, rotations do not work unless we rotate around a point that is not the center. It will rarely change anything. Reflections will move us across the axes. Translations move us along vectors. And dilations will either enlarge or reduce our figures based upon our scale factors. That leads us to the question, true or false? All circles are dilations of one another. All circles are dilations of one another. Well, that would be true, because if I have a circle and I were to dilate it, I would just create larger and larger circles or smaller and smaller circles, which means that all circles will be dilations of one another. They all just have different radii, and since they're the same shape, we can dilate them. Since there's no corners, circles just have an infinite amount of corners, or 0, depending on which way you want to look at it, which means that since they have all these little corners, or no corners, that they're always going to be the same shape, which makes this true. All circles are just dilations. And if all circles are just dilations of each other, does that mean that all circles are similar? Well, if we think back to the definition of similar, similar figures are figures that look the same but are different sizes. So yes, this would be absolutely true. All circles are the same, they're the same shape, but they all have different sizes based upon their radius. So therefore, they would all be similar to one another. They just all have different dilations that are occurring. All right, next up, we have some definitions that are specific to circles themselves, different parts of circles, different things that you'll see around circles. And we'll be covering these throughout Unit 8, so you'll see lessons on congruent chords next. You'll see lessons on secants and tangents down the road, but these terms are extremely important, and you'll be seeing them quite a bit as you continue in math. The first one that we have is chord. A chord is a line segment, important that's a segment, with endpoints on the circle itself. So in this case, segment AB is a chord. Now, some important things about chords. Chords will always have both endpoints on the circle. So there will always be 2 endpoints for a chord. It's always going to be a line segment that creates a chord. And a chord will always have the points lying on the circle once again. So extremely useful information here. Now there's going to be some properties of chords that we cover in just a little bit that we'll talk more about. Next, a secant or secant. A secant is a line, ray, or segment that passes through a circle. Line AB is a secant. Now, the main difference here, a secant is a line, ray, or segment that passes through a circle. Again, a chord has its endpoints on the circle. So while line AB is a secant, segment AB is a chord. Now I can't create a chord without a secant. So secants and chords will always go together. Now again, very important, a secant needs to pass through a circle twice. It needs to pass through it at least, it needs to pass through it at most and at least 2 times. It just needs to pass through it twice. It must. in order to be a secant. Secants will have their own various properties, and oftentimes you'll be dealing with secants and chords together, like I was saying earlier. Next up is tangent, probably one of the most important pieces within circles, one of the most important things that you'll learn because of its uses in calculus. A tangent is a line, ray, segment, or curve that touches a circle at a single point. So again, it only touches it once. It doesn't cross through my circle. It just touches my circle on its way past. And this is extremely useful, this tangent line. It's going to be used constantly as you improve and get better at math. And again, tangent lines, they only touch. That's their one key point. It's only one point at which they touch. If it crossed at 2 points, well, that means that'd be a secant. But since it only touches at one single point, that makes it a tangent line. Tangent lines are useful for whenever you're trying to find out a slope or anything like that on a curve at a very specific point in time. Tangent lines allow you to find that. And that's why they're so useful, is because you can find the slope at any specific time frame along a curve, which allows you to find out very precise times, very precise speeds. It allows you to find out very, very, very precise measurements. And that's why it's so useful. So tangent, again, a line, ray, segment, or curve that touches a circle at one single point. Lastly, we have the point of tangency. Well, we keep talking about this one single point. That one single point is called the point of tangency, the point where the tangent touches the circle. In this case, point C is our point of tangency. All right, let's go ahead and expand a little bit upon chords and what we can do with chords. So, oftentimes when we're dealing with chords, we're going to deal with problems that deal with from the center to the chord. So we're going to be looking for the distance between the center and the chord itself. So that's oftentimes what we're dealing with here. Now, whenever I draw a radius and it intersects my chord, so I draw a radius, I'm planning on it going through the chord, then it will bisect my chord, meaning it will cut segment XY perfectly in half. Further, it will intersect segment XY at 90 degrees. So it intersects at the midpoint, but it's also an altitude. So very useful here is knowing that when you need to find the distance between the center and a chord, you can draw a segment to that chord and it will always intersect at 90 degrees and it will intersect at the midpoint. Now further, I know that OX and OY are radii because they go from the center to the edge of the circle. Obviously, this green segment isn't a full radii because it's not going all the way to the edge of my circle. So that's the main difference that you need to watch out for. But this will allow us to solve for these triangles. And of course, this green segment is congruent to itself. So therefore, these triangles are congruent to each other by side, angle, side. And again, this will allow us to find out a lot of information around these secants and around these chords and around these circles just by knowing this information. Further, a radius that bisects the chord, so that often happens whenever I draw a radius going through my chord. A radius that bisects the chord is also a perpendicular bisector of that chord. So it also will intersect it at 90 degrees and cut it in half. And again, this is happening any time that we have a chord within our problem. We can do this. So properties of chords, this will always work for chords. So let's go ahead and try out a sample problem with this. Example, hint, make right triangles, connect the radii. It tells us circle X has a radius of 15. We want to find the distance from point X to our chord. So we want this distance here. Now, first off, I know that segment XD is a radius. So I can go ahead and draw that radius in and say that it has a distance of 15. Further, if I draw a radius from the center going through my chord, I know that I'll split CD in half and it'll also intersect it at 90 degrees. So therefore, since it's splitting CD in half and CD is 24, means that it's giving it 12 to each side of this triangle. So now looking at this, I have a right triangle. I have two sides. I have a side of 12 and a side of 15. I'm going to go ahead and call this last side y. And that way we can solve for it by using Pythagorean's theorem. So let me go ahead and expand this triangle out. I just need to change one of these variables here. So this would just be, in this case, y instead. And that would give us y squared plus 12 squared equals 15 squared. Well, 12 squared is 144, 15 squared is 225. So we're left with y squared plus 144 equals 225. From here, I can subtract 144 from both sides. That'll give us y squared equals 81. And then, of course, from here, we want to get y by itself. So we're going to go ahead and take the square root of both sides. What I do to one side of my equation, I must do to the other. Doing so will give us y equals 9. And that will be our final answer. So therefore, we finally know that y is equal to 9. Therefore, the distance from our center to the chord is just 9 units in length. Meanwhile, the distance from the center to the edge is 15 total. So you can see how we get different numbers for the distance to the chord and for the distance to the radii. All right, next, let's go ahead and cover some properties of tangents. So properties of tangents, these are extremely important, extremely useful. The radius of a circle will always be perpendicular to the tangent line. If I draw my radius to the point of tangency, where the tangent line intersects our circle, it will always be perpendicular. It will always create a right angle. That is an extremely important property of tangents. It's used all the time. So make sure that you guys have this one down. If I draw a radius to my tangent line, it will always be perpendicular. The other property that we have is if I have two tangent lines here, I can see that they're tangent lines because they only intersect at one single point. And those two tangent lines share a common endpoint. Well, that would make those two tangent lines congruent to each other. So AC would be congruent to BC here. So again, if they share a common endpoint, I know that those two tangent lines will be congruent. Next, let's go ahead and talk about some specific lines and specific tangent lines within circles. The first one is lines of center. Then we have common internal tangents and common external tangents. As we can see, we have three different lines here. We have line PQ, we have line XY, and we have line AB. Now for line of centers, it would make sense for the line of centers to be a line that connects the centers of our circles. So looking at this, we have P as a center and Q as a center. So PQ must be the line of centers because it's connecting the centers of our circles. Next up, we have common internal versus common external tangent lines. Of course, these are both going to be tangent lines. And the word common just means that it's shared by two circles. So common just means that two circles have it. Of course, we can see that XY touches both circles at one point. Same with AB. The only difference is internal and external. So when we talk about internal, it means that it's in between the two circles. When we talk about external, it means that it's outside of the two circles. It's not in between. So in this case, the only line that's in between the two circles is XY. The line that is not in between the two circles would be line AB. So our common internal tangent is line XY, and our common external tangent is line AB. All right, let's go ahead and try a couple problems to finish off today's lesson. The first one is dealing with common tangents, what we just talked about on the previous slide. Of course, I see a common tangent here, a common external tangent, segment AB. So we have some steps that we're going to follow. If we follow these 4 steps, we should be able to solve for segment AB. The first step is to join the centers. So I have point Q and point P. I'm going to go ahead and draw a segment between the two, and we should know that distance between the two of these. Again, the radius from point Q to the edge is 18. The radius from point P to the edge is 8. So therefore, QP is 18 plus 8, or 26 in length. So let me go ahead and just draw that on here. This is 26 in length. Further, Both angles A and B are right angles because they are intersecting the tangent line, and these are radii. QA is a radius and PB is a radius. So therefore, they'll be 90-degree angles. Step 2, draw radii to the points of contact. Now, we already have that. We already have those drawn. They were given to us, so we don't need to do that step. BP and QA, those are both drawn to the points of contact. When they say points of contact, they're just talking about the points of tangency. So next up, number 3, through the center circle, draw a line parallel to the common tangent. So I'm going to draw a line that's parallel to segment AB until it hits the radius of the larger circle, making a rectangle on top and a right triangle below. So here we go. There's my right triangle. And then here's my rectangle. Since this is a rectangle, I know that opposite sides will be congruent. So if this is 8, this must also be 8. If the full thing is 18, and I've used 8, then the rest must be 10. Further, rectangle, opposite sides are congruent. If AB is x, then this segment must also be x in length. Now, I have a right triangle down here. If I have a right triangle, and I also have two sides, a side length of 10 and a side length of 26, that means that I can use Pythagorean's theorem to solve for our third and final missing side, x. And if I solve for this x, well, that'd be the same as segment AB. So that'd be the end of this problem. So using Pythagorean's theorem, I'll have x squared plus 10 squared equals 26 squared. Of course, 10 squared will be 100. 26 squared will be 676. From here, I want to get x squared by itself, so I subtract 100 from both sides, give me x squared equals 576. Lastly, to get rid of the square, I take the square root of both sides of my equation, giving me x is equal to 26. So therefore, the common external tangent, AB, is equal to 26 units. The last problem that we have today is a walk-around problem. And you'll see these quite often. Both the problem that we just did and this problem you'll see over the next few weeks as well. So for the walk-around problem, they also give us a hint. And you'll notice that it's a walk-around problem when you have a circle and around it you have a quadrilateral with each side having a point of tangency. That's how I know that I'm going to do this type of problem. So the hint that they give us, label the side or piece of the side you are looking for as x and start walking around the problem. Now, it doesn't really matter where you start with this, but you're going to label a side as x and then you start moving around the circle. So looking at this, I know that AB is 10, BC is 15, and AD is 18. I can go ahead and start by labeling up each of those sides. Now, we want to find the length of CD. So what I'm going to do is I'm going to go ahead and call part of one of these segments x. So I'm going to say from point B to my point of tangency is x in length. Now, if this is x in length, this other side must also be x in length because both of these are tangent lines and they share a common endpoint, meaning that they must both be congruent. So if this one is x, this bottom one must also be x. So let's go ahead and draw that all in. So again, I got all those 10, 15, and 18. I got those from the side lengths given to us. And I just called this x and x. Now, if the full thing is 10, this is where we start walking around. If the full thing is 10, and just this piece is x, well then from A to our point of tangency would be 10 minus x. And if this segment is 10 minus x, the other segment must also be 10 minus x. Because again, both are tangent lines and they share a common endpoint, point A. Next, I continue walking around. You have the full side length of 18. And I have from point A to the point of tangency is 10 minus x. Therefore, from point D to the point of tangency will be 18 minus 10 minus x. Well, I distribute the negative through my parentheses. That'd give me negative 10 and positive x. 18 minus 10 is 8. And then I have plus x now. So both of these are 8 plus x in length. Now, I want to continue walking, but I don't know this distance, CD. That's what we're trying to find. So I can't continue walking because I don't know this full distance. So I go back to my start, and I start walking around the other direction. Well, if b to the point of tangency is x, and the full thing is 15, then c to the point of tangency would be 15 minus x. And same thing with the other side. That would also be, let me go ahead and draw these congruency symbols here. That'd also be 15 minus x. Because again, they're both tangent lines. They both share a common endpoint, endpoint C. So they'll be congruent to each other. So now at this point, I have CD. I don't know what the full thing is, but I know it's 15 minus x plus 8 plus x. So CD is equal to 15 minus x plus 8 plus x. Now something interesting happens here. When I combine my like terms here, I have a negative x and a positive x. Those will cancel. And that's why it's so important to distribute the negative through the parentheses. I know it's just a negative sign, but it's very important that you distribute it through. So the x's will cancel, and that will leave us with CD equals 15 plus 8, which will give us 23 units as our final answer. So the length of CD is 23. All right, thank you guys so much for watching today. If you have any questions, please let me know. Appreciate you guys taking the time to watch this video. Have a great